Okay, welcome everyone to the power of electric snakes. Today we're going to be talking about PySpark. PySpark is a Python library that combines the easy to use nature of Python with the power of Spark. So I'm sure you've seen a number of sessions already in Summit that focus on these tools separately, and we're going to talk about them together today. So my name is Brad Llewellyn.
And my name is Kendra Reed. And yeah, so as Brad mentioned, we were talking about PySpark, and you may have seen PySpark used in various different technologies, such as Jupyter Notebooks, Databricks, Synapse Analytics, machine learning. So we'll dive a little bit into that today and talk a little bit more about it.
Also, before we get into that, please explore what PASS has to offer. PASS is a phenomenal organization. I've been a part of it for years. No matter where you are in the country, or even in the world, there's very likely a local group near you. A lot of them are remote now because of COVID, but please either attend locally if you can, or attend their remote sessions, and reach out to them to speak as well. They're great opportunities to get together and gain valuable speaking experience. Also, larger events like SQL Saturdays and past marathons are always going on as well. So please get involved in those. Again, great opportunities for speaking experience, great opportunities to volunteer, as well as opportunities to see past quality sessions, summit quality sessions any time of year from the best speakers all around the world. So definitely get involved in that. And then finally, PASS has virtual groups that are typically tailor focused either around languages or subject areas. So an awesome opportunity for you to network with people who share the very specific interests you do, as well as, again, see some sessions that you might not see anywhere else. Also, evaluations are critical to feedback for Kendra and myself, so we can understand how to present better as well as tailor our content to what you want to hear. Also, feedback is critical to PASS itself, allowing them to understand what sessions you want to hear and what presenters you want to hear more from. So definitely take that time. As wherever you are in the world, please get out and vote. It's very important.
And also, we want to make sure that we express that the views that we talk about here during this presentation is solely ours, Brad and I's, and is no way affiliated with Microsoft or the Fast Track for Azure team. And so a little bit about Brad. So Brad is a data analyst architect, as I mentioned earlier, and Brad has been doing this for some time now, about 8 years. And some of those past events that he's talked about, he's actually the former organizer for the Charlotte BI group, and is a frequent speaker here at Past Summit. You can find some more about Brad here at any of these social media locations, or he has a fantastic blog, Breaking BI, that definitely should check out, after our presentation.
Thanks, Kendra. So a little about Kendra. Kendra is also a data analytics architect. We actually work on the same team. We live 5 minutes from each other actually, which is a great coincidence. He's a phenomenal open source contributor. Honestly, he's the open source guru on our team. Anytime we have questions about Spark or Python or Linux, we always reach out to Kendra because he knows everything. Um, he's been around about the same amount of time I have, and if you're interested in more about him, you can reach him at Kendra Reed on LinkedIn or at his K-Reed OSS. Before we get to it, an interesting anecdote I always like to talk about Kendra is Kendra and I actually met before we started working together and had no idea who each other was. He and I met at a volunteer event here in UNC Charlotte, where we were mentoring grad students on kind of how to have careers as analytics professionals. And we met each other, and then I went on leave and came back 6 months later to after having some kids, and Kendra's on the team, and I'm like, with a name like Kendra, I was like, do I know you? Like we've met before, haven't we? And he was like, yeah, man, of course we've met. It was just a great opportunity to see how such a small world it is. So
Yeah, that was a crazy coincidence there that happened. But who know, our paths crossed again, and even for the better. So, um, So today we'll be talking with you guys about RDDs versus data frames. What are those? How are they the same? How are they different? As well as we'll walk through some data and do some data science preparation, right? So we're going to be cleaning some data, making it more usable. And then after that, we will go into some data science modeling, right? And so Brad will walk you through those, and we'll talk a little bit about each of these areas as we go through.
Oops. Computer's running a little slow. There we go.
All right, so today to go through this, we'll be using a Databricks notebook. And with this Databricks notebook, we're using Python. If you're not familiar with Databricks, definitely should check it out. It's a pretty common use for data analytics. However, these the code and stuff that we'll be using today can be used in any type of Python notebook, Jupyter, or if you're using, Azure Synapse, Spark, or anything like that, you still can use the same set of code and go through that. So first, we got to have some data, right? So to play with. So it looks like we're loading in some adult data here. Brad, you want to talk a little bit about that and what is this data that we're using today?
Sure. No, thanks. So this is, if any of you have seen any of my presentations before, you definitely recognize it. I use it pretty much all the time. It's the Adult Census Income Binary Classification Dataset that I love to say in its full name. It is a data set that's readily available in a lot of Microsoft products. It's right here in Databricks as well, so you can see it's part of the default data sets available, and it has a bunch of different demographic information about individual people. So things like age and gender and their work class and their education level and all that sort of stuff. And then at the very end of that data set, it also has a binary classifier for how much their income is, whether it's less than 50K or greater than 50K. And that's what we're going to do today. We're going to step through that data set and ultimately build a predictive model and evaluate that model to understand how well we can predict a person's income based on all those other demographic features. So
Cool.
before we step into those other pieces, we'll walk through just a little bit of what's happening here. A lot of this might look Greek to you right now because we haven't gone over much of this. You'll understand much of this as we go, but we won't cover every bit. Basically, the code here, which you can dig through on your own, shows us how to build an RDD and a data frame from that base data object.
Okay. So let's jump right in. So RDDs versus data frames, right? So um, I see that we're starting off here. You talk a little bit about how we use it, using collect for the RDDs and show for the RDDs. So do we have some examples of that, of the differences there that's being used?
Sure. And after we're done with this, perhaps you can tell us some of the underlying mechanics that differ between the two as well.
Mm,
So collect is what we typically use to show an RDD. And as you can see, once we do that, it comes out looking a lot like an array, like a typical data object. So we've got an array, and it has these parentheses in it. These are technically called tuples, and we'll see them a lot more as we go. But basically, every row just gets kind of smashed together into these tuple objects, and that's what an RDD is. It has very little structure in that way.
mm.
And we also have show for data frames, which we can actually scroll out here because the zoom does give us some compaction issues. But as we scroll out, give it a second, we will see that this will eventually start to resemble a table.
Mm. Yeah.
And this table has rows and columns,
Hmm.
just like any table does. So while it has much more structure than we'd expect from an RDD, it's also more limited in that you know exactly what shape this is going to have. It's going to have rows. It's going to have columns. Those columns are going to have data types and whatnot. So
Yeah, and I think that's one of the biggest things that you pointed out there is the differences between RDDs and data frames is in tables. Well, RDD is a little bit more obscure on how you see the data when you run that command. However, from overall perspective, data frames are seen to be a little bit faster in computation, and we can get into the garbage collection and serialization, how they work between the two. But overall, it's much easier to use data frames as we go through this. You'll see to manipulate and extract the data as it would be with a RDD.
Awesome. I think my computer has finally caught up now to
And,
the.
and one point out that I probably should have said is that RDD, in case you don't know what it means, is resilient data set. Is kind of the full term there. I know a lot of people just say RDD. But
I think your audio might have cut out there, Kendra. It was resilient distributed data set, right?
yes. Oh, my bad. I'm losing some audio there. My bad.
Yeah, not a problem. Not a problem. So, something else that's interesting that we always like to call out. If anybody's ever heard of the MapReduce technology, we're going to see that same terminology here when we're dealing with RDDs. So kind of the first thing we like to show is if we want to select a new column from an RDD or create a new column, we use this map terminology here. And it has a lambda function as well that Kendra is a huge expert on as well. But when we use this, we basically tell it, okay, I have this R object and it doesn't care what this R object is. In our case, the RDDs are a collection of tuples. So we're just accessing an element within that. So we say I want the 0th element because Python starts at 0. And I want the 12th element, since Python starts at 0, this is actually the 13th. I want to multiply that by 4. And then I have to bring out the first few records, and that's just top 5. So as you can see, we again have another array of tuples because this is another RDD. Except now our tuples only have 2 values, the 0th value and the 12th value times 4. And we have absolutely no idea what these fields are because they're not named because the RDD doesn't have column names. Comparing that to the SQL syntax, which while requiring some additional functions to import, it does have a little bit more power because it allows us to use field names. So we can say I want to make an hour per month column, and I want its value to be hours per week times 4. And then I just want to select the age and hours per month columns, and then we can show those as well, and they come out in a nice table format.
Yeah, and you may notice that after each of those commands there, that Brad ran some type of show or display command there, some type of action. He ran top with the RDD and ran show with the data frame, and that's because Spark itself is lazy in this evaluation. So when you have transformations, which is what these first commands are before the show here, what it does is it kind of saves up those computations and then and then executes them with the show. So some benefits of that is it makes it a lot more easier to manage from a Spark perspective. As I mentioned, it saves computation and increases speed, and it also helps reduce the complexity between how much has to be done at runtime, and overall it helps optimize the Spark from the long-term benefit.
That's interesting, Kendra. I think I'll start using that line with my boss. Anytime she calls me lazy, I'll just say, no, I'm trying to be more efficient.
That's a good one. That's a good one.
So another thing we'll go down to is the other half of the MapReduce. So map, as we saw, is very similar to a select. It allows us to manipulate the shape of our RDD and determine what fields and whatnot we want to pass through. Reduce allows us to do aggregations. So in this case, we want to calculate the total sum. And we have another awkward syntax here. Whereas map brings in this random R object, reduce brings in 2 objects. So it has this T object, which stands for total, and you can name these whatever you want. They're named with 1 letter here because that's a pretty typical syntax, but it's by no means the only way. And then H is the object we're bringing in from the previous function. So T defaults to nothing. It has no value, and then H is the previous record, in this case, the 12th field, or field 13 since we're starting from 0. And it just says I want to take the total and continually add every H to it over and over again. So this adds every 12th field to T until it eventually outputs a single value, which actually equals the sum of something. It's sum of field 12, which we don't know what that is. Looking down at the data frame, we have the same exact operation, except this time we're saying, let me group by nothing in this case, and then just give me the total hours per week. So we calculated the same exact number here that we calculated above. The difference is the SQL syntax is starting to get a lot more readable.
Yeah, it's definitely a lot more readable, and I think couple of things to point out there with the RDDs with DataFrame. It's like the RDDs takes a little bit more time from an operations perspective to perform just simple grouping and aggregation operations versus the DataFrame, which is a lot easier to read, to start off with, and also it's faster overall from just finding the data and analyzing it. Excuse me, analyzing it. It's overall just better way to go about it.
Interesting, interesting. So let's get a little bit more complicated. So we know that when we're doing operations, we almost never just group by nothing and say, give me the total sum. We always want the sum by this field, sorting by this other field, and all sorts of these options. So we can get a little bit more complicated here. Dropping the reduce, we can do an aggregate by key. So what we ultimately want to do is we want to group by a field called education. See that right here. And there's a very specific syntax you have to use for this. In order to do that, so we need to map our records down again into a very specific tuple. So education must come first. This R3 is our education field, and it has to come first. And then we want to take our R0 field, which happens to be age, and we want to aggregate that by the key. So what's actually going to happen here is Spark is going to rip this R3 field out and assume it is the key because it's the first field there. And so now all we're left with is a single field. So we now no longer have to subset that because it's only a single field. It just takes a single scalar value. And what we want to say is we want to start with a value of 0, 0. That's what's going to go into our W. Just like the reduce had a starting value, aggregate by key has one too. And then our R is going to pull this R0 down. So then we say for the first element of W0, I want to just add. We saw the same logic before. So I want to calculate a sum. And then for the second element, I want to add 1, which means you're counting. So you're calculating the sum and the count, storing that in a tuple. And this is called W because it's very interesting. Kendry's going to enlighten us in a minute to kind of the context around this, but Spark uses partitions. And this is called the within partition aggregation, meaning that this will actually take place locally on every compute. And we'll have multiple W's that come out the end of it. And then this second set needs to aggregate all of those partitions together. So this T value, again, defaults to this starting value, and then P actually pulls down the values from above, pulls down this W, actually. So to calculate our total sum, we need to just add all of our individual sums together. And to calculate our total count, we need to sum all of our individual counts together. And then that will give us this output here. So we actually take that one step further because nobody really cares about the sum and the count. What we actually wanted was the average. So we take that same code and we put another map on top of it. And this map says I want to take R0, which is the education value. And if you looked very carefully up here, you noticed the key gets plopped out first as the first element, but then you have another tuple afterwards, which represented that T. So the first element of the tuple is the sum, second element's the count, and we have a tuple within a tuple. So we access that as 1, 0 and 1, 1. And again, we can always calculate the average as the sum divided by the count. So with all of that work to calculate an average, we do eventually get our result here. And obviously the data frame syntax for assembling SQL is much simpler with just the group by and then the average, but giving us ultimately the same results in the table format.
It's amazing how you have to, do 10 lines of code, and within 5 lines, you can drastically read it and improve the overall process. But yeah, I mean, to go back to your point about the partition. So yeah, Spark uses partitions in order to help distribute data and make it a little bit more easier for it to manage it. So what happens a lot is when you are performing your operations, depending on what is being done, your data is being swapped between those partitions. Sometimes it has to collect the data, switch to a different partition, depends on what is being done. So what Brad talked about with those partitions is kind of start looking at those partitions and getting the data that it needs to complete the operation. Sometimes it's good to have more partitions. Sometimes it's good to have smaller partitions, depending on what you're doing. But however, that is a parameter that you can also config on your cluster that you're running your Spark computations on. You can set the parameter of how many partitions that you want to use for those operations.
Perfect. So to round out the kind of analysis we've been going so far, let's look at one more thing. Scrolling down, and again, you'll have this at your disposal. It's part of the included materials. So if you want to dig through this field by field, you're more than welcome to. But let's look at how a join works. So as you can probably expect, RDD syntax for this is complicated. So joins in RDDs use keys just like the previous aggregate by key did. So in this case, I want to join the RDD we just created. So the one that has education and then the average age back onto the original data set. So in order to do that, I need to map my original data set, putting the first element as education, just like before, because it's always going to assume the first element's the key. And then I'm only allowed one additional element. So I have to wrap everything else. Notice it's 0, 1, 3 is skipped because 3 is up there, 4, 5, 6, every other element in a tuple. And then I join that to my other RDD, which is already formatted with the key first. And then what the end result of this is actually even more nested. So we can actually scroll up and look at that from the previous example. What we ultimately get is we get our education level at the top level and just inside the first tuple, and then we have a tuple. So we actually have 3 levels deep here. So we actually have to unnest that entire thing, eventually getting back down to our original format, which shows all of our fields in the original order plus the average age at the end. And as we can see with RDDs, following a more SQL syntax, it is significantly easier, only 2 lines of code.
Yeah, it's very, very easier to do it that way. I think, one of the things to point out of why it's so much easier with data frames is the RDDs is more of a low level type transformations and action that you're performing on your data set. So it's going to take a little bit more to get the data out that you need. It's kind of like low level programming, if you're using Java or something like that. If you get below that, when you're running your MIPS assembly language or something like that, you're at the lower level programming, and that's why RDD seems a little bit more complicated. All right, so we're getting into the data science now. Okay, so I assume here we're going to be cleaning up some of the data here, right, Brad?
Yeah, we're gonna clean up this data, but as I'm sure you know, the first step is always to look at your data, right?
Yeah, might want to know. Might
So
want to know what's there first.
yeah. So there's actually an interesting function that I always like to show before people hop into the cleaning itself, called describe. And again, we're going to zoom out, which I hope doesn't take as long as it did the first time. But when we zoom out, we can actually look at all of our data in a tabular format.
Mhm.
And we're going to get to see a few things while this progresses. So what describe is going to do for us is it's going to create a view where we can see the mean, the standard deviation, and the max and min values, as well as the count of all observations for every field. So when we do that, we get a good look at our data set. And again, I apologize that it's taking a little bit longer than usual, having some latency on my machine. Barring the size issues here, I'll zoom in just a little bit and show you. What we see here is the first line is the count, followed by the next line, which is the mean, and we do have some wrapping there that does obscure it a little bit. But basically, for instance, there's 32,561 age values. It has a mean of 38.5, standard deviation of whatever, going down. What's very interesting is as we look across, so let's take work class, which is the second field. So while it might be difficult to see, if we look for min and then look 2 spaces to the right of min, we see that work class's minimum value is actually a question mark. It's very interesting. There's some other things we see if we look further over. For instance, capital gain has a maximum value of 99,999. That's very interesting because when we see that, the first thing we think of is, hey, is this an outlier or not? And we'll dig into that here in a minute.
Cool.
Zoom back in and scroll down, and let's take a look at how to do this. So when we actually want to see the individual fields themselves, which is always a good second step, we created this set of code here. And what this set of code here does is it just groups by the field name and it counts it up, and then it sorts that in the descending order of the count, or the descending order of the field actually. So we get to see the maximum value first, and we see this giant gap between the maximum capital gain and the capital gains lower than that, as well as having this huge count there as well. So it looks like there's some sort of funny business going on that we want to investigate, and maybe we would ultimately remove this field or change it in some way.
Cool. And so, right, when you're going about this cleaning up data, what process do you use? Like you pointed out that you believe that there's some funny data here. Is it just inclination, or do you just have a process that you go through that this 159 may not seem to be accurate just because you know the data already?
So it's a really good question. So it's half intuition and experience, and then the other half is industry expertise. So that's why it's super important to have subject matter expertise on your specific data set. In this case, just a regular person can look at this field and understand there's a huge gap between these 2 values.
Yeah.
And there's a large number of occurrences of one of them. So something just feels off.
Yeah.
If we scroll down and look at hours per week, it presents a more interesting problem that we might not be able to solve with just intuition. Notice how hours per week also caps at a very awkward value. It caps at 99, which again should set off red flags. But it also has values at 98, 97, 96. It just so happens that the count for 99 is a little bit higher.
Yeah.
So what's happening here? We can't say because we didn't collect this data set. We don't have that level of expertise. But if we were doing this in practice, it'd be very important to get a really good understanding of what's going on there, because those might be outliers that need to be resolved.
Would that 80, at the bottom we have 80 and 133. Do you believe that is an outlier as well? Since it's such a high count, right? Maybe that might be something we need to.
That's something I never even considered when looking at this data set. That's a good eye there. So I don't know. You're right. There is a tremendous number of people that put 80 as a strict value, which could come down to the way it's reported or something like that. But again, these are phenomenal questions to ask the people who are collecting the data and ensuring that we understand where this is coming from, because the difference between a good model and a great model is going to be understanding those little subtleties.
Right. And I see this a lot where customers want you to tell them about their data, right, and want you to modify their data, understand their data, but you're just reading it once or twice, coming in and helping them, and it's all about who uses the data most daily, most likely can give you the most insight of that data if something looks off, right? So you definitely have to have someone that has a keen eye on the data that they're working with.
Yeah, that's a really good point. So let's hop down just a little bit for 1 second and look at something interesting. So if we hop down to cell T1, we're about to get that question mark issue that we called out earlier. So here we have the field native country, and we want to do the same type of aggregation here, and we notice that its minimum value is a question mark. We could scroll through this data set, and we have before, seeing kind of what question mark might mean, but our intuition, again, not understanding the underlying context here, is that this is kind of an unknown field. And it's probably personal preference, but I personally don't like having special characters in field names, because you never know what sort of system you might be using where those special characters might not be allowed. Now all of a sudden you've got to make drastic changes to your workflow. to accommodate these characters.
Mm-hmm.
So we scroll down a little bit more past all of this analysis that we would do if we were stepping through piece by piece, and we see that we can actually replace this. So we're getting a lot more complicated at this point. We're actually starting with some base Python functionality, which is let's make a array and let's loop through it with a for loop. So that's not even PySpark. There's nothing PySpark involved in that. However, then we get in our data frame and we use that same with column we've seen before. We want to make a new column. This column is going to be called the original column name. So for instance, native country underscore 0 in this case. And then we're just putting a kind of when clause on it, or an if clause that says if the field value itself is question mark, then I want you to replace it with unknown. And in a very interesting syntax that maybe Kendra can explain to us a little bit, instead of most other languages that will just have an optional third parameter for the false option, Spark actually requires us to use this otherwise function. So we have when and then dot otherwise, which requires us to then tell it what its false is going to be, which will just give us back the original field. And we can see down here that we get our underscore u fields, and we've dropped the original fields out of the data set entirely.
Yeah, I think with that when and otherwise, I kind of liken it to if you're using, some other programming like Java. So when you have to use the if else and then maybe a then type of statement, where you have to provide, if none of these matches, then what do I do? And so here we're saying that, we want to fill it with that column if, it doesn't match the question mark, that we want to use what's already there instead.
Interesting. So let's scroll down a little bit. Again, there's a ton of analysis here that you can look through at your own leisure if you'd like. But let's dig into an example that's super common. So something we often hear about is dummy variables, or in Python it's often called one-hot processing, where we want to take a text field and turn it into numbers. So most, maybe not most, but a lot of machine learning algorithms don't like text. They want math, they want numbers, they want things to be nice and easy so you can put them in math formulas. So obviously a field like male female is going to be very difficult to do that. So what we often do is we want to turn this, and with only these two values, you could technically get away with just making female 0 and male 1, or vice versa. But when you get into more fields, it does more values, it gets more complicated. For instance, let's say we had an unknown sex as well, and you gave it a value of 2. So then could you say that unknown is twice as male is female? That doesn't, from a mathematical perspective, that makes perfect sense. Two is twice as many ones, but that doesn't make any sense from our perspective. So we actually want to break it out
there.
We actually want to break it out into kind of a 0-1 field for every possible value. And in order to do that, we have some functions we'll dig through here. So the first thing we'll do is we need to be able to calculate a array of just these values, and that's actually more complicated than you might imagine. You have to distinct it out and then turn it to an RDD, and then you have to do something called flat mapping to bring that back out to a base Python object. You have to collect it again, and now we have an array that we can use to loop through. And then we're going to get some really interesting syntax here. So we saw a for loop before, but this is something I actually learned myself whenever I was putting this together. Is about these ability to build arrays on the fly using for loops. So Kendra can certainly enlighten us a little bit more about that from a Python perspective. But what we can do is we can actually say, I want to build an array here, and then here's what values I want my array to take. So I want it to take that same when value again when the original column itself takes the value I'm looking for. And remember, our values were defined right here. So when it's taking the value I'm looking for, give it 1, otherwise give it a 0. And I want you to alias this new column as the original column name underscore the value we're looking for. So for instance, sex underscore female, sex underscore male. And I want you to do that for every possible vowel in vowels. And that gives us this this particular column. Here.
Yeah, yeah. I think that array on the fly there kind of helps you simplify, what needs to go into that array. And also, I think something to point out here is if you look at the syntax, actually, it kind of looks like, you know, case when, then it kind of looks like you're using SQL syntax, right? I mean, it's very similar to what you would do with a SQL statement. When completing these operations. So a lot of times you can see what is being completed as Brad had outputted here when you're executing these statements and what's being done at the base level of the operations, right? So this is more of a high level programming that we're using here, and then once we get down underneath, these are the actual commands that's being ran.
Yeah, I wonder if they have a clever name for SQL under a Spark context. So we also have a bit more around that same point. Something that's interesting, as Kendra called out, this looks like SQL, but notice at no point here did I tell it what data set to apply these on. These are effectively SQL statements, but they're not being applied to any particular data set just yet. So what I can actually do is I can use my select functionality to say I want to select, and sorry, let me zoom in a little more. I know we've been playing with the zoomed out version for a while. And of course, as we zoom in, we have to scroll back down again.
Mhm.
Sorry about that. So as we see, we can actually select the original column values here. And then we say, and I just want you to add these new calls onto there. It's just a plus sign, which is super interesting because I've never seen another programming language where you can just kind of add on additional column selection statements like that. So it's very interesting.
And I think it's pretty neat with, PySpark, how you're able to just inline run these SQL statements, with that, right? So this select is an actual select statement essentially that you're running, and the drop is an actual drop statement on that table, right? So you got to think back to the data frames when we talked in the beginning, where the adult underscore DF is an actual table. Now we could, most certainly run the actual SQL command within this line, but you can also use the programmatic way of doing it as well. That's what Brad is showing here.
Interesting. So we have slightly more complexity we want to add here. So let's take this same thing we just did, and let's say I want to apply that to every single string field in my data set. So obviously, I'm just as lazy as Spark. So my goal here is to just programmatically do all of this. I don't want to manage any of it. So we can use that same interesting syntax we saw before, creating an array on the fly, but there's even more complexity we can put in there. So we can say, I want to add an if statement. And what's always interesting to me is how these things are almost built in reverse from the way you typically say them.
Yeah.
So it says, I want to take this C0 value, which we don't know what that is yet, for every C in the adult df.dtypes function. And what that actually outputs is it outputs two values. It outputs the field name, which is C0, so we want all the field names. And then the C1 is going to be the data type of the field itself. So I'm saying I want to do this for every field that starts with string, or every field whose data type starts with string. And then that gives us all of these fields down here, even including some of the underscore U fields we modified earlier.
Right.
So it gives us a complete list of all the fields we might want to loop through.
Oh, that's cool.
Now let's put it all together. And when we put it all together, we can say I want to loop through all of these string fields, and I want to do the same vowels function, same exact code we saw before, build the sets of unique values. Then we have our column creation statements we're going to create. Then we have our select, where we add those columns to our data set and drop the original columns. And out the other end comes a giant data set, which if we look at our Spark result here, we actually see we have two fields plus 108. So when we started with 30-something fields, we now have 110 fields in our data set.
Wow. Wow.
So before we get to the modeling, the very last piece here is we have to come up with a label. So the label column, as some of you might be aware, is the column we're trying to predict. So in our data set, we originally had a field called income, but since we did our one-hot processing, we now have two income fields. We have an income less than or equal to 50K and income greater than 50K, both of them taking 0, 1 values. So that's perfect for a binary classification example. That's what we want. However, if we were to try to predict income greater than 50K using income less than or equal to 50K, it'd be a pretty easy problem to solve because we know they're going to be opposites every time. So we actually need to drop one of those to make our analysis useful. And in our case, we're just going to drop the less than field.
This is cool. All right, so now that we've cleaned up our data, got it all nice and pretty how we want it, dropped the the unknown values and cleaned those up. So now we're going to get into a little modeling of that data, right? And right, I know this is your expertise of the area of doing some modeling and machine learning off of it. So what's the first step here? What are we going to do first?
So this is where things get really interesting, and you can tell us some of the context behind the scenes about why Spark does ML differently. But in most machine learning applications, at least most of the ones I've ever used, you start by basically giving the algorithm two sets of data. You say here are all the fields I want to use to build my algorithm, and then here's the field I want to predict, or the fields I want to predict. Spark, for whatever reason, says, no, I'm not going to let you do that. You need to give Spark two fields and only two fields, which means you need to take all of your features, as they're called, everything you want to use to predict, and you need to put it in one column. And you need to take all of your labels or targets and put them in another single column. In our case, we only have one label, so it naturally fits one column. But in order to put all of our features in a single column, we have to make what's called a vector. So in order to do this, we have a vector assembler that Spark gives to us. And we can say, I want to take all of our input columns except for the one label we want. Understanding we've already dropped all and transformed our data to our heart's content, and we want to call that vector features. And then we want to, again, because this is just a column creation statement, we want to use that to transform our original data set. And then we just want to select out those two fields, and then we can go down and look at our vector here. Now having this row syntax with our label first, and then this features column second. So digging into this features vector, it's actually really interesting what this does. It's very clever. So instead of having 108 individual fields, which would obviously take up a tremendous amount of space when we're processing, instead we have this vector. The first value is 108. So this is the number of fields we have, 108 fields. And then we have 0 and 39. That means that the 0th field had a value of 39. The first field had a value of 77,516, all the way. And notice we start skipping values eventually. Go 2 to 4, and then 5 to 14, 14 to 23. All of those fields that are being skipped have a value of 0. So Sparse Vector basically says if we have a data set that has a lot of zeros, we need a much more efficient way to store it. So it stores it by index and value, assuming anything that's not explicitly listed here has a value of 0.
That Spark is pretty neat underneath to know to do that, to kind of speed up that overall processing there.
So, Kendra, kind of a question back to you. Obviously, Spark's this huge network. How does Spark have built-in ML capabilities? Like what are we using here?
So for here, I believe if you scroll back up there, I think we pulled in here. Yeah, so we pulled in one of these libraries here, PySpark ML feature, right? So this is what you can consider, and I go back to Java, if you're importing a class or object, this would be the same same thing where, I'm looking at the ML feature library and I'm going to import the vector assembler class. So that's how you can pull in these different features, um, for features for to be used within this notebook. So we kind of did this before too, and some of the other steps above where we pulled in some of the SQL commands and those pieces. But if Brad was to take this out, this code wouldn't run. It wouldn't run at all because it doesn't know where to start from. So in order to do this, we have to pull in this library and use this class in order to process this.
So Spark's been pretty clever so far in the way it processes large amounts of data. But I feel like the naming has been a little awkward. We talked about the sequel, and I'm wondering, we being clever people, if we wanted to name a machine learning library as part of Spark, what do you think we could name it?
I'm not sure. What would you name it?
Oh, well, we've got our clever sequel within Spark SQL, obviously.
Yeah.
Wouldn't it be nice to call it Spark ML? But
Yeah.
no, let's not do that. It's interestingly, it's called ML lib or ML lib, depending on who you want to
Right.
you ask about it. But
Yeah.
Spark has a number of features under the covers, and while it's incredibly clever in the way it's designed, the naming conventions themselves are always a little comical to discuss. So scrolling down, once we have our features together, we need to now build our classifier. And earlier that we skipped over, we actually already split our data into testing and training sets, which we won't get into. But we actually want to do more of that clever Spark lazy evaluation here of let me build a base model here and then apply it to a data set. So we're building a GBT classifier, gradient boosted tree, which is definitely one of the more common and more powerful algorithms. And we want to say my features column is features and my label column is nt gt50k. We want to fit that against our data set and we can kind of see what the result is here. It's a whole lot of not very useful information, stuff we already knew, number of features, number of classes. It does tell us the number of trees, and those are just default values there. But where it gets more interesting is if you scroll down a little bit more. It's whereas many other languages might have like a .predict function or something like that. Spark, in its awkward naming conventions as always, uses .transform. So you want to transform against your testing data set, and that pops out our predictions here, which again shows that sparse vector. But what's really interesting is we have another vector down below, but this is a dense vector. So before we were dealing with RDDs that had all of these tuples. We're still getting in these nested tuples at this point, but we're starting to get names, so at least things are a little bit more readable. And this dense prediction vector has values that aren't between 0 and 1. So these aren't probabilities. This is some other value that doesn't have a strict scale. But fortunately, these raw predictions aren't really for our consumption. It gives us this additional probability vector at the end, which says that this particular record has a 95% chance of being the first value and a 5% chance of being the second value, which means it predicts 0. 0 in this case meaning it isn't greater than 50K or it is less than or equal to 50K. So finally, what we need to do here is we want to compare our models. We want to be able to do some evaluation. Obviously, we can't just pick the first model we run. We need a little bit more diligence there. So interesting, PySpark also offers evaluators. And this evaluator is very interesting, as we'll see before. This binary classification evaluator doesn't care what data we are giving to it. It only wants two things. It says, give me a raw prediction field, or column in this case, and give me a label column. And it's going to compare those. It's going to compare the predictions to the actual values. And then we can apply that evaluator to whatever we want. So we can say, evaluator, I want you to evaluate my gradient boosted tree using ROC and using precision recall, which we won't dig too much into right now, but they are two different metrics for comparing different types of models. And we can see that our what's commonly called AUC is about 91%, and our area under the precision recall curve is about 79%. And those values themselves don't mean much because their purpose is to compare to each other. So what we really want to do here is build multiple models. So we can build a couple more models, and again, with the great programming efficiency that Spark has, we can actually reuse almost all of our code. So all we're doing is we bring in a new model, in this case logistic regression, use basically the same code, except it's called logistic regression now instead of a GBT classifier, and then we use literally the same exact code below, just swapping out the LR prefix. And the same evaluator too. We don't even have to recreate our evaluator, and then that gives us the evaluation metrics for logistic regression. Same exact thing for naive Bayes. Then at the very end, we can build a nice little Python dictionary that outputs all of the results side by side so we can compare. And basically, we see that our boosted decision tree has about 91% AUC. Our logistic regression comes in slightly lower at about 90%, and our naive Bayes is bringing up a truly terrible 36%. We can also see a similar trend with precision recall, in that we have 78% for boosted, 76% for the logistic regression, and paltry 19% for naive Bayes. So we see that the boosted decision tree and logistic regression are very close and could probably use some optimization to make a better model. Naive Bayes, there's something very wrong there. We need to reevaluate whether we want to use it.
And so when we're looking at these models, Brady, maybe you can. This is getting a little bit out of my realm here with the machine learning. What is the ideal percentage that we're looking for here? To know that, I know we have 91% with the boosted decision tree. Do we want it to get it closer to 100? I mean, or one, should I say? Is that the best?
Oh, that's what a question. So one thing I always like to call out is if you ever get a metric that's 100% says this model is always accurate, you've done something wrong. Your model better not be 100% accurate, or something's not right. But as far as how good is good enough, that's a hard question. And it's again, it goes back to the thing we talked about at the very beginning. This part is intuition. It's basic math. I, without any context of this problem, could understand that 91% is better than 90%. What I don't know outside of the context is whether 91% is good enough. There are a lot of applications where, like, if you want to display an internet banner to a certain type of customer to get them to buy your product, 91% would be pretty good, because a banner is pretty low cost to put a banner on a website, and it gets seen by so many people, you're going to get a great lift no matter how low that is.
Yeah.
But if this was a 91% chance that you convicted the correct person of a violent crime, you need to be a little bit higher than that, right? You don't want to be wrong 1 out of every 10 times.
Yeah.
So it really depends on the context of the problem. So that is a phenomenal observation.
Yeah. And so I assume, 6 months from now, when I have more data, I probably need to go back and rerun this, right? Because my scores could probably change. Now, this is not something that's going to stay stagnant forever, right?
Now you're asking the real good questions. So that's definitely what we do a lot with customers. Honestly, is anybody can build a predictive model. As you saw, it was just a few lines of code here. It's not hard to build a predictive model. The key is building one that, one, solves your business problem, and 2, is going to solve it in the future. Because if you look at software development teams, it's pretty common to build something and then try to throw it over the wall. Say, okay, I did my development job, I'm done. When the real value in any sort of algorithm, any sort of application or whatever, is how long can you keep it running effectively? Because the longer it runs effectively, the more value it's providing. And that does mean that as your data changes over time, as trends change, you have to come back and redo this process. Whether it's in an automated fashion or in a manual fashion, you've got to go back and reevaluate these models, retrain them to make sure that they're using up-to-date data and that they're not predicting this year's fashion trends using 2 years old fashion data.
Cool.
So let's hop back over to the slides real quick.
Yeah, so we definitely thank you guys for joining us today and walking through. We talked a little bit about the difference between RDDs and data frames. We talked about, once we have your data, how to clean it up, make it a little bit more readable and more usable. And then we jumped in a little bit into using that data to do some predictive analysis, right? And how you want to be able to, choose the right prediction. The models that Brad showed there aren't the only models that can be used. There's plenty of other models out there, and you could build your own model. And how to, and you can use those things to do, like I said, some predictive analysis there. And I think one thing to point out as well, we talked about PySpark here, but when you're working with Spark in general, there's other languages as well, right? So you have Scala, you have Java, you have Spark R that you could use. So there's different ways to go about solving the same things that we did here today.
No, that's definitely right, Kendra. And again, thanks so much everybody for listening. Thanks to Kendra for showing up for this. He wasn't originally
Super.
on the schedule, but definitely wanted to try out a slightly different format here instead of just one presenter talking at you for an hour. Have kind of some conversation back and forth. If you want to reach out to either one of us, we've got our Twitters there, and you've got my email address. Like I said, I'm more on the ML side, and Kendra's got a super deep expertise on the open source side with the Python and the Spark and the Linux. So if you have any questions, feel free to reach out. Otherwise, at this point, I think we'll pass it over for questions. Much.
Thanks, everyone.